So I'm Rachel Harrison. I'm a postdoc here at Monash, and today I'm going to be talking about my work on protoplanetary disks, specifically looking at polarized emission at millimeter and submillimeter wavelengths, and seeing what that can tell us about the properties of the dust in those disks. So as folks have talked about in previous talks, the field of studying protoplanetary disks has really exploded over the last few years. We can now see all of this interesting substructure in the dust emission of disks. And we've got evidence that planet formation is already well underway in disks like these through finding circumplanetary disks and also through finding disturbances in the gas flow created by embedded planets. So these disks are only like a few million years old, which means that dust has to grow, or solid material has to grow many orders of magnitude in size on what is a pretty short time scale in terms of astronomical processes. So in addition to the continuum emission and gas emission that I showed on this slide, we can also find polarized continuum emission coming from the dust in these disks, particularly at millimeter and submillimeter wavelengths. So all of the images you're looking at here were made with ALMA data. These are all protoplanetary disks taken at a wavelength of 870 microns. So in these images, the vectors represent the direction of polarization. And I think in all of these, they're also scaled so that the length of the vectors represents the polarization fraction. So you can see that in all of these disks, we've got kind of a similar polarization morphology, where you've got all of the polarization vectors parallel to the disk's minor axis. And that's very consistent with polarization from scattering. So in this case, that would be the scattering of thermal emission from dust grains by other dust grains. And what's interesting about that is that it gives us an additional way to gauge the sizes of the dust grains in these disks. So determining dust grain sizes is important because that affects our estimate of what the remaining mass reservoir of dust in these disks is, which affects, what types of future planet formation can occur in these disks. So one way to measure dust grain sizes is to look at the spectral index of the emission, and from there derive a dust opacity index, and then derive a dust grain size from that. And that's pretty simple if you can assume that the dust is optically thin, and under that assumption, these spectral index measurements imply dust grain radii of around a millimeter. On the other hand, with scattering, what you can do is that, so the wavelength where the polarization fraction from scattering peaks depends on the maximum dust grain size of the disk. So you can see in this image on the right that as you go to larger and larger dust grain radii, the wavelength where that polarization fraction peaks gets longer and longer. So if you look at dust polarization at multiple wavelengths, you can constrain a maximum dust grain size, and these observations tend to imply a maximum dust grain size of about 100 microns. So that means we've got an order of magnitude discrepancy between the grain size estimates that these two methods give you. So one thing we can do to try and start resolving that discrepancy is to look at disks in polarization at much higher resolution, so that we can see how things like the dust substructure within the disk affects the polarized emission. So this is from a Nature paper that I was on that came out last year. This is HL tau with ALMA at 870 microns. And this is at a resolution of, I think, about 4 AU. So you can see we've got a ton of polarization vectors, and you can see that the polarized emission is correlated with the disk substructure. And that becomes especially apparent if you zoom in. So here I've got some of the gaps and rings in the disk marked out. And you can see that in the gaps, the polarization fraction is higher than in the rings. And you've also got sort of more of an azimuthal pattern. So the direction of these polarization vectors starts to curve more around, that elliptical shape of the disk in the gaps. Whereas in the rings, most of that emission remains more parallel to the disk's minor axis. And you can quantify that more if you take like a cut of polarization fraction and intensity along the major axis of the disk. So this is polarized intensity and fraction versus distance from the center of the disk along the major axis. And again, you can see that the polarization fraction is higher in the gaps. And that has to do with the changing optical depth in the disk. So the disk is more optically thin in the gaps and more optically thick in the rings. And in order for you to observe some net degree of polarized emission, you have to have some degree of basically radiation anisotropy in the region surrounding a dust grain. So imagine if you had a dust grain embedded in a very, very optically thick environment where it basically sees an isotropic radiation field coming in towards it. It's going to scatter light isotropically, basically in all directions, and you're not really going to observe any net degree of polarization. So that's why in the more optically thin regions of the gaps, we see a higher polarization fraction. And so changes in the direction of the radiation anisotropy also affect the polarization angle. So if you're a dust grain embedded in a ring, you're mostly going to see emission coming towards you azimuthally along, basically along the direction of the ring, and less emission coming radially towards you. So that's what results in this pattern in the rings where the polarization direction is along the disk's minor axis, because that's the radiation that's been scattered at 90 degrees into your line of sight from within the rings. On the other hand, if a dust grain is in a gap, it's mostly going to see radiation coming in towards it from the adjacent rings, which creates this more azimuthal pattern of polarization angles. Yeah, so with this, really excellent data on HL tau, we did some modeling of the polarization in the disk. So this model actually combines polarization from scattering and polarization from grains that are aligned in a way that they're effectively prolate. So in other words, the long axes of these grains is aligned along the orbital direction within the disk. And basically the reason why we went with that model that includes the aligned grains is because we found that in this model, basically with scattering only, with the types of dust grains we were using in the scattering only model, we weren't able to fully recreate this more azimuthal pattern in the gaps. So this model includes spherical dust grains with a maximum size of 100 microns. So again, we're kind of still back to that same problem of the discrepancy between maximum dust grain sizes that you derive from polarization and the maximum dust grain sizes that you would derive from looking at the spectral index. So something I'm currently working on to try and resolve that discrepancy is looking at scattering from porous dust aggregates. So these are aggregates made of smaller monomers that aren't completely solid. And if you look at this plot at the bottom, this is showing polarization fraction times the effective albedo versus wavelength. You can see that solid dust grains, which are represented by that black dashed line, have a very narrow range of frequencies where they'll emit a significant amount of polarized emission. Whereas if you look at dust grains that aren't completely solid, they'll produce polarized emission over a wider range of wavelengths. And this could also help explain, why it's so common for us to see polarization from scattering in protoplanetary disks at wavelengths of around ALMA band 7, so like 870 microns. I think it's more likely that you've got dust grains that are emitting polarized emission over a wide range of wavelengths than that all of these diverse disks just happen to have very, very similar dust grain sizes. Yeah, so these are some models that I made using MC-FOST. These are models of polarized emission in HL tau with two different dust grain populations, one with dust grains that are basically 90% empty space, one with solid grains of the same size. And you can see that the porous dust grains produce a significantly higher polarization fraction. Yeah, so I know I've only got a minute left, but these are observations of another disk. So we're now seeing this same type of correlation between polarization and disk substructure that we saw in HL tau in a second source. We just need a third, and it's officially a pattern. And I'm also working on modeling dust grain polarization fractions from different dust aggregates using a few different codes that numerically calculate scattering properties for irregular grains. And the ultimate goal of this is to find a dust grain population that can consistently explain both the polarization spectrum and the spectral indices in these disks.
So you began with the discussion about the differences in the grain sizes from the emission models versus the scattering models.
Mm-hmm.
And I thought you were going to explain that emission models were the original thing was optically thin, and that's a bad approximation. But then you started talking about this porosity as being a factor. So I'm wondering, at right this point, what is the resolution? Is it primarily optical depth, or is it porosity?
At this point, I think we're not really sure what the ultimate resolution to that would be, but there also has been some work on, basically you can somewhat resolve this discrepancy if you look at higher resolution images of disks as opposed to looking at lower resolution images where you're kind of smearing together emission from optically thin and optically thick regions, which would affect your estimates of the spectral index.
Hi, Rachel. In your images of the model of HL tau, when you compare porous versus compact grains, it's harder to see if there is an azimuthal ring pattern within the rings, the gap. Sorry. So is this a problem or not?
Right. So in the outer region of HL tau, in the outer region where you do have that azimuthal pattern, so the color bar on this is percent polarization, but that outer region actually is, I think, a gap in the disk. But yeah, we would need to make basically we need to zoom in on these models to see more clearly the correlation between polarization fraction and disk substructure.